Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are in AP Chemistry class doing Unit 3 according to the College Board units, not the other tape, which is according to the book. Okay, so we're going to be talking about intermolecular and interparticle forces. So the first thing is, what is the difference between inter and intra? These are inter, so what are they? Inter it is between. Inter, whoops, I need to make it right. Inter means between. So these are between molecules. Okay. The other one, intra, is within. So what we've been talking about so far has been intra. It's been bonds within atoms. And these are much stronger. Now we're going to talk about that we have these little molecules. You can think of them as little lumps, which is molecule in Latin. And sometimes they have positive and negative sides to them. We've learned that they can be polar. Well, those positive and negative sides can attract other molecules that are floating out there. Everybody can imagine that? So we're going to talk about how molecules react with each other, not undergoing chemical reactions, but just how they interact as they're floating by. Okay, everybody got that in your brain? Okay, so we're doing intermolecular forces. A lot of times these are abbreviated IMF, not International Monetary Fund, but intermolecular forces. Okay, so how does the strength of these intermolecular forces in general compare with these intramolecular forces, the real bonds, ionic, metallic, or covalent? Which one do you think would be stronger, a real bond or these forces between molecules? I think somebody said real soft. The real bond is stronger. So intermolecular forces are much weaker than ionic, metallic, or covalent. Okay, so here is an example. We have chlorine and hydrogen ions, a little hydrochloric acid there. And each one of these, you remember that hydrogen is a WIMP, and it gets its electrons stolen all the time. And chlorine is extremely electronegative, so it is going to hold that electron stronger. So even though we have a shared covalent bond, they're sharing a pair, the chlorine gets the electron a lot more, the pair a lot more, and it ends up with a partial little dipole negative, and the hydrogen gets this little partial positive charge, right? And then as it's floating around in the liquid, this negative gets attracted to this positive, and this little force of attraction gets there, which is indicated by a dashed line. So that's that on your AP test. If you draw a dashed line, they know that that means a force of attraction between those chemicals. Everybody good so far? Okay. So, referring to the diagram at the right, discussed the difference in the strength between the attractive forces A and B. A is a real bond. It's a covalent bond. B is this intermolecular force. So A is a covalent bond. Okay. It has intramolecular forces. B is intermolecular forces. And A is much stronger than B. Much stronger. And one thing that indicates it, that we can look at, is if we look at the boiling points, that is an indication of the strength of these forces. Things that boil easily, they very easily go from liquid to flying off as a gas, don't have much of these IMFs holding them down. But if they have strong IMFs, then they're not going to want to boil. They're going to want to stay as a liquid. So here, this is the enthalpy, that's the heat of vaporization for hydrochloric acid. So this is the energy to convert from liquid to gas is 16. So that's just the bonds. This little hydrochloric acid it was a liquid. Now it's evaporating, it's going to fly through the air. We don't want that to happen in our lab. We don't want it evaporating and then drying out and getting super concentrated or anything like that. But that's how much it takes, 16 kilojoules per mole. The bond of enthalpy for HCl, so this is the energy required to break that bond, and now we've got hydrogen gas flying out and chlorine gas flying out. Look how much bigger that is, 431. So that reflects that strength. You can see that this covalent bond is much stronger than these little forces of attraction that we have in this diagram. Okay, that's the most important thing. So another thing about this, last year my kids did really good. They understood this real well, and I think it was one of the keys that they did good on the AP test. So we're going to make sure you understand it too. Now, explain how our data does it. Intramolecular forces are greater than, less than sign, than intermolecular forces. So bond enthalpy is greater than enthalpy of vaporization. Breaking a bond is greater than just something vaporizing. Okay, so here's another little chart out of your book. This unit for your book is chapters 10, 11, and 12. We've already read 12, so we're going to just be adding some 10 and 11 to it. I can get you there. I got the chart. Yay. All right. So here we can see the melting point, the numbers, the energy it takes to overcome covalent bonds, metallic bonds, ionic bonds, dispersion forces, and so versus intermolecular forces, IMFs. That's what we're studying right now. And we're going to learn about 3 different kinds, really 4. We're going to learn about London dispersion forces are called LDFs. Dipoles and hydrogen bondings. But you don't have to worry about that now. Just think about, look how much bigger these numbers are than those numbers. Okay? Got that in your head? All right, so now let's talk about it. What conclusion can we make? In the first 3, the real bonds that are broken. Okay? This requires much more energy. In the last 3, the intermolecular forces are just overcome. We're not broken, we're just overcoming. And this requires less energy. Okay? Good so far? Getting these concepts in our head? All right. The 3 types of intermolecular attractive forces exist between neutral molecules. They are, so we're going to learn about each of these 3. The first one is called London dispersion forces. And I always thought, well, maybe they discovered this in London, so we got Big Ben here, just like we could discover it in Atlanta and call it Atlanta dispersion forces. No, that was the guy's last name. It was Mr. London, so that was a little disappointing. Okay, but good for him. The next one's called dipole. That's kind of fun because you say it twice. Dipole. And the last one is called hydrogen bonding. Okay, so we're going to talk about why these have an effect and what they do. So everything in chemistry, really in the world, works because of energy. So if you don't know the answer is always energy. Okay, and so there is energy, electrostatic, positive and negative interactions can be described by Coulomb's law. And that's where it is charges in the numerator, distance in the denominator. And the bigger the charge, because it's in the numerator, the more force. The closer it is, the more force. The farther away it is, the less force. The smaller the charge, the less force. So my son, Eli, who goes to Kennesaw, was telling me not only did Coulomb come up with this knowing about electricity, and a unit is named after him, the Coulomb, and understand all this groundbreaking stuff in chemistry and physics, He also did engineering, and he was telling me how he figured out this way to figure out something about soil and making buildings. How could he have done everything like that? That just seems a little unfair. Mr. Coulomb's like grabbing up all the science. We're going to be famous in chemistry, and physics, and engineering. Let's be famous there too. So I had no idea that he has some big soil way to figure out your soil so you can build a building on it. Anyway, that's an aside. I was just impressed by him. Okay, so this is sort of summing up what I said. The attractive forces increase as the magnitude of the forces, that's the size of the charge, increases, and the attractive forces decrease as the distance increases. So you're going to have more force, bigger charge, less distance. They're inversely proportional. Okay, based on your answer to this part, all of this kind of goes a little bit in order in your book. I changed it to be more like that, but when it talks about pages or parts, that kind of is referring back to your book. Based on your answer, give 2 specific reasons why intermolecular forces are weaker than ionic bonds. So the charges with intermolecular forces are much weaker. So it's less because these Q's are smaller numbers, okay, than in the bonds. And also the distances are greater. So that D is bigger. Bigger denominator equals smaller number, right? Mathematically. Okay. So here he is. That's his name, not his city. In 1930, we should figure out what city he did this in. Fritz London proposed, it'd be funny if it was London in Atlanta, proposed, but I bet it wasn't, proposed that the motion of electrons in an atom or molecule can create an instantaneous, I want to say instant, an instant, because that works, we don't really have to say instantaneous, an instant or momentary dipole moment. Okay, so let me explain that to you. Imagine that this is just a neutral little molecule floating along. But then something happens, say it gets close to some sort of charged thing. So it gets close to maybe like a polar molecule that had a negative end. It gets close to it, and all of its electrons, remember they're in clouds, they can go where they want to go. They feel that negative and they're like, ugh, negatives repel, and so they all scoot to the other side of the molecule. They make a little scoot. And when they do, it makes this side positive and this side more negative. And even though this is normally kind of neutral everywhere, it's got scooty powers where it can scoot. It has just for a second, for an instant, it can have a positive and negative side, okay? That is called London dispersion forces, or is abbreviated LDF, okay? So that's our first one we're talking about, and all molecules can do this. Everybody's got LDFs. So on the AP test, when they tell you to describe all the forces on a molecule, step 1, LDF, everybody's got them, okay? Scooty forces, can you imagine the Scooty forces? Don't write Scooty forces on the AP test. Say it more scientific, okay, like we're gonna say here. Describe what can happen in an atom or molecule when the distribution of the electrons can be arranged asymmetrically, so they scoot over and get asymmetrical, even for an instant. They can affect the electrons in another atom or molecule. They scoot, causing an instantaneous dipole that causes more dipoles. So it sort of has a chain reaction. When somebody scoots, everybody does a little scooting, okay? Scooty forces, London dispersion. You can imagine people scooting around in London dancing. Okay, and everybody's got it. Everybody dances. Okay, define polarizability. You have to emphasize that I think. Polarizability. And explain how this property is related to the relative strength of the dispersion forces. Polarizability. Does it become polar easily? Does it scoot easily or not? Everything doesn't scoot equally, okay? So polarizability, the ease at which the charge distribution is distorted. Some get distorted easier than others. More polarizable molecules have larger London dispersion forces. Larger dispersion forces or London dispersion forces. Okay, good so far? Type 1 of intermolecular forces, good? Okay, so here's a little graph that you can kind of see. Notice that we have neon, argon, krypton, and xenon. And as you go down the graph and they get bigger, then the boiling point increases. That means they got more forces holding them together, more LDS. And notice that here, those are noble gases, but even the not noble gases, fluorine, chlorine, bromine, iodine, we look at this halogen, we see this same trend. That as they get bigger, they've got more London dispersion forces, and they don't want to boil, they want to stick together. Because they're getting stuck together by positive and negatives when they scoot. Okay? So, this is our trend that we can see. Let me find my right page. Okay, dispersion forces increase within, so London dispersion, same thing. They just increase within the size of the molecule. They get bigger, these forces are more. And the reason why is bigger clouds are more squishy. They're more polarizable. Molecules with bigger electron clouds have stronger. So a lot on the AP test, you have to write these explanations. So these are some buzzwords that you could use in explaining one of these questions. Okay, notice this would be wrong. X has a higher boiling point than Y because of its mass. Is this about how heavy it is? No. This is how big its electron cloud is and how squishable it is, not how heavy it is. So a better thing to say is to say it's more polarizable, or it is, it has a bigger electron cloud, therefore it is more affected by a temporary dipole on another molecule. Okay, so next. Here we have some molecules. These are all C5H12. Okay, so they all have 5 carbons and some hydrogens. But they have different shapes. And these are called isomers. And they have different names too. And I don't know if I need to teach you about naming organic. I think I do. I think at the end we might do a little mini organic unit just so that you know a little bit more about what I'm talking about. But isomers is where it's got the same formula but a different shape. It's not that we're just bending it around so it looks different. Bonds have been broken and reformed. We've chopped the end off of this and attached it there. Can you imagine that, like with Legos or something? And this one, we chopped off 2 ends and stuck them both in the middle. Okay, like that. So these are different chemicals. They have different properties. They have different names. They're just made out of the same exact stuff, like how you can make different things out of Legos. Okay, so we want to know which one do we think would have the highest boiling point and the lowest boiling point. Do y'all have any guess? Which one do you think is going to have more forces? And which one's going to have less? Any ideas? What do you think, Kevin? You think which one's going to be the highest one?
I think it's C.
You think C will have the highest boiling point? Why do you think so?
Because it's more spread out.
It's more spread out. Okay. Well, it turns out this one's more spread out. You're right that it has to do with spread out. This is balled up. And a ball has less surface area than something squished. Like if we have Play-Doh and we made it into a ball, it'd have a certain amount of surface area. If we squished it out into a sheet, it'd have more. Does that make sense to you? Okay. So this one actually has less surface area. This has more. So you were exactly on the right track. You just didn't name the right one, but you had the right reason. So this one has the largest surface area. So it has more. It has the most dispersion force, and it has the highest boiling point of all of these. This is in the middle. This one has smaller surface area, so it has weaker dispersion forces, so it has the lowest. boiling point. And that one's in the middle. Okay, number 2. So that was A, was London. This is B, dipole, dipole. This is our next kind of force. Excuse me. All right. So next, dipole, dipole happens in polar molecules. So these things are not polar. They're all carbons and hydrogens. They don't really have, like that one is symmetrical. It doesn't have positive and negative ends. That one's symmetrical. All of those are non-polar. These are polar, things like water, okay? So here we have, it says draw the structural formula of 2 CH3s, CL3 molecules, label the positive and negative ends, use dashed lines to show the forces. Remember I told you dashes equals these forces. Now I drew it for you so you wouldn't have to bother doing this. I was trying to figure out how to speed this up. All right, so we know that hydrogen is weak, and it's going to get a little plus, right? And this hydrogen is going to get a little plus. And we know that chlorine has got high electronegativity, so it's got a little negative there and a little negative there. So what's going to happen is opposites are going to attract, and this negative and that positive are going to get attracted to each other. That should be dotted. Let me try to do it better. Whoop, whoop, whoop. We're fun with sound effects. All right. Dot, dot, dot. It's going to make a little force. And if we look at the polarity of these molecules, it looks like that, right? So this is a dipole-dipole. It's not for just a second. They haven't scooted. They're bonded where there's a positive and a negative side. Follow that? So this is stronger. So the chlorine, I'm going to go back to red. I think it's a little easier to see. The chlorine is more electronegative, okay, than the carbon, and so it has that negative. And this is because they are polar. Polar molecules, and why are they polar? Because they are asymmetric. Okay, good? Can I scroll? Can I scroll all the way up? Okay, so let's look at these two. Which one's going to have the higher boiling point? Which one's polar? Is this one polar or non-polar? Is that one polar or non-polar? Non-polar, because why? It's symmetrical, isn't it? And it's all carbon and hydrogen. That's a hydrocarbon. They are your classic non-polar. So this one is going to have the lower boiling point. It's not going to have those attachments. It's ready to go fly off. That is propane. And you know that propane is very volatile. This is definitely polar. It has the higher boiling point. Okay? So we're going to compare them. On this side it is polar. On this side it is non-polar. On this side it's asymmetrical. That one's symmetrical. This one, the dipoles don't cancel out. So sometimes, you know, you have something real symmetrical, it all cancels out. Here, these oh so symmetrical, the dipoles cancel out. Okay, these bonds are not neutral. It's not bonded to itself, but they all cancel out. So this one only has London dispersion forces. This one has London dispersion forces too. Remember, everybody gets London, and then some of them get other stuff to make them stronger. So it also has dipole-dipole. It's fun, you get to say it twice. So therefore it's stronger. Okay, so now look at these trends in boiling points. This little graph here out of your book. Okay, so here, first we're going to just look at the bottom one. So this is looking at the carbon family, carbon, silicon, germanium, tin, and they are all bonded exactly the same to 4 hydrogens, but as they get bigger, notice the boiling point goes up. Everybody follow that trend? Okay, So explain this trend. All of these are nonpolar. Okay? They're all tetrahedrals. They're all symmetrical. They all have London dispersion forces. But the trend is because larger molecules they're more polarizable and they have stronger London dispersion forces. So they're bigger, so they got more. They got more forces, yes.
Okay, I have two questions. What is a dipole?
What's a dipole? Dipole is where it's a polar molecule and it has a positive end and negative end. And each end is called a dipole. So water, like you got water, let's draw a little water here. Whoop. So water always is negative on the oxygen side and positive on the hydrogen side. So this has got a polar end, it's got a negative and a positive end, and so therefore it is ready to make a little bond with another water where this negative will be attracted to this positive, but it won't do that on just one side. It's not just dipole. On this side, this is going to be attracted to another negative, so it is dipole-dipole. So great you say it twice. One for each side, yes. Mm-hmm. And if you get caught, tell them that you don't have a Minga pass. So I'm not going to stop. We got to keep going here. All right. So now we saw it got bigger and it was stronger. Now, notice over here, we got three weird things that are not following this trend. They're doing it here. As it's getting bigger, it's higher and higher, boiling point. But over here, we got this weird little whoop. Everybody see the weird whoop, 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 whoop? Okay. Why is it doing that? This is our next type. So we know about London dispersion. Everybody's got it. We know about dipole-dipole. Polar molecules have it. And now this is our third one, hydrogen bonding. And the three that are weird is water, HF, and ammonia. Okay? Water, HF, and ammonia. Why? This is our third one, so this is like C, hydrogen bonding. Now, what is hydrogen bonding? It is another intermolecular force, and it's an attraction between hydrogen with in a polar bond, especially HF, HO, and HN, and a non-binding pair of an electrons. So it is a hydrogen cuddling up to an unshared pair. But it's got to have a bonding requirement. Okay? Everybody imagine that? It's what's happening in water. Okay? And so who it's cuddling up to is a nearby small electronegative ion bonded to F, O, or N. So everybody think about FON. What does it bond to? FON. It's almost a word, right? FON. Got to have some FON bond. Okay, so this shows what it does. So here you've got two ammonia molecules. And did I draw this for you? That would be nice of me if I had. That's good. I didn't draw it for me. I need to make a new key from mine from yours. Okay, so here's ammonia. It's got this beautiful, big concentration of negative in that unshared pair. So that's a big old negative. This hydrogen is positive because nitrogen is more electronegative. It's a bully. They're sharing some electrons, but it gets them most, so it makes it sort of positive over here. And so you end up with a hydrogen bond. The hydrogen is going to cuddle up to the unshared pair. And so that's very strong, not compared to a bond, but of these intermolecular forces, that's the strongest of them all. Okay, so that's the hydrogen bond right there. Hydrogen bond is that thing right there. Okay, so next we are going to circle the ones that can do hydrogen bonding. Now notice the hydrogen has to be on FON. We gotta have an unshared pair, We gotta have a polar molecule. It can't be nonpolar. And the hydrogen has to be on fine. Everybody got that? Okay, so let's look at it. Do you think this one can do hydrogen bonding? No, because the hydrogen is on the chlorine, not on fine. You see that? We have unshared pairs, but no fine. How about that one? No, hydrogens are on carbon. We have unshared pairs, but it's not on fine. How about that one? Yes, because you've got unshared pairs, and you've got hydrogen. It's not symmetrical. It's all bent looking, and it's got hydrogen on an oxygen. Okay, how about the next one? Is this one gonna work? No. How about that one? Yay! Look how much y'all have learned. Because the hydrogen is on the nitrogens and we got unshared pairs. Okay? Feeling good so far? Okay. Now, how does this explain why water expands when it freezes? Why does ice float? It's because water, H2O, or you can think of it as HOH, it's got hydrogen on the oxygen. The oxygen has unshared pairs, so we have hydrogen bonding going. On each one, the positive hydrogen cuddles up to the unshared pairs on the oxygens, and it makes these hydrogen bonds in a circle of 6 water molecules. When it does that, to a line like this, it has to spread out. And it makes a little hole in the middle. See where you can put your finger in the hole? So there's a little air pocket in the middle of each little group of 6. And so that little air pocket is why the ice floats. It's got all this air built into it. It's also why snowflakes are always 6-sided. It's reflecting that little circle there. Isn't that cool? Okay, so the H bond makes it spread out. It causes a cavity, a hole. But in a liquid, they stick together harder and there is no hole. They're free to move, so they're sticking harder. They're not forced to spread out and be still. Okay, so there's one fourth one. You think of there being 3 intermolecular forces. There's sort of a fourth one. We'll call it D, and it's called the ion dipole. And you already learned about this in honors when we learned about how salt dissolves in water. Do you remember that? And on your notes it said, Mickey Mouse attacks, because the water will attack the salt and pull it apart and surround it. So here we have the positive ears. So what's in the middle? Is that the sodium or the chloride? It's the chloride. We got a negative chloride there. So what goes here? What lines up with the oxygens? The sodium, the positive sodium. Okay, so y'all remember that from honors? Did y'all learn about that in Cordon's class? Y'all learned about that? All right, good. So all atoms and molecules have London dispersion forces. Only polar have dipole-dipole. Okay, only a molecule that has hydrogen bonded to fine will do hydrogen bonding. And only if it's an ionic substance dissolved in a polar solvent will you get ion dipole. Okay, feeling good about all this? All right, I think y'all seem to be doing good. Let's apply it some. Okay, so we've got 6 things, and we're going to figure out their boiling point. Remember, the volatility reflects what forces we got going on. Okay? And these are the things we're going to keep in mind before we put these in order. First of all, ionic real bonds are stronger than these forces. So one of these is ionic, so it's going to be at one end of our strongest to weakest. That nonpolar has less forces on it. It's going to be less forces, it's going to be volatile, it's going to be ready to go fly off and be a gas. Okay, smaller is more likely to fly off than something that's bigger, because bigger's got more electrons to get entangled and to react with others. Dipole is stronger than London dispersion, and dipole is weaker than hydrogen bond. Okay, so now let's apply it. Let's look at what we got. So first of all, we've got methane. Methane is little and nonpolar. Okay, everybody agree to that? We've got this calcium oxide, which is ionic, right? So those are probably going to be our two ends. Okay. Now let's look at the other ones. Okay, this one, 1-propanol, right here has where it can do hydrogen bonds. Okay. And if we look over at this one, 1,3-propanediol, I'm sure I said that really good. It's got two of them. Is 2 better than 1? Yes. So it's got 2 hydrogen bonds places. Okay. Okay, this one is also nonpolar. It's symmetrical. It's all carbons and nitrogens. So it's nonpolar, but it's bigger. So that's what we're going to think about with that one. And this one has this little end that's got a charge. So it's got dipole-dipole. Okay, so let's put them in order. We will start with the one that would be the 161, the one that is going to fly off first. Who's going to fly off first, do you think? It's our methane, so he's number 1. And we know the one that's going to fly off last is our ionic, right? That one's 6. I have a salt crystal lamp over here. I never worry about it flying off and deciding to be a gas. Ever. It's going to sit there, okay? But if it was some methane over there in our pipes, it wants to fly off and be a gas, doesn't it? You turn it on, psst, you hear it. So there's our ends. Okay, what do you think is going to be number 2? That was 1. What's 2? Nonpolar but bigger, right? Wouldn't that be the next one? It's the same as this, just bigger. So that's going to be number 2. Our propane is 2. We'll put it at the ends right here, 2, and circle it. Okay. So now, what is going to be next? So which is stronger? Which is a stronger bond, hydrogen or dipole-dipole? Hydrogen, right? So our number 3 is going to be this dipole-dipole. Now we've got 2 hydrogens. Which is stronger, to have 1 hydrogen bond or 2 hydrogen bonds? 2. So our next one, our number 4, would be the 1-propanol. And our last one, our number 5 one, before we get to ionic, is that one with 2 hydrogen bonds. So you could do that if that was the AP test, right? Could you logic that out and put it in order and then tell them why you did? And talk about polarizable and electron clouds and intermolecular forces. All right, so now let's move on to liquids. So we are going to be talking, so let's talk about viscosity. Have you ever heard that word viscosity? You hear about it on motor oil commercials. They'll say, buy Valvoline with less viscosity breakdown at high temperatures. So viscosity is thickness of a liquid. You want your motor oil to be thick. If it gets thin, then your parts are going to start rubbing in your engine. So we want it thick. So viscosity has to do with this. So with these forces. And viscosity is the resistance of a liquid to flow. It's how thick it is. Thick and slow. Now, why would decane be more viscous than hexane. Decane's got 10 carbons, it's big, it's heavy. Hexane's got less carbons. Both are nonpolar, both are made out of just carbon and hydrogen, both are symmetrical, but the difference is that decane is bigger, it is more polarizable, and therefore has a greater viscosity. The bigger and more polarizable it is, the more it's going to have a bigger viscosity. Okay, so now, why do you think glycerol with 3 OHs is more viscous than propanol with 1 OH? What does it have more of? Hydrogen bonds, right? It's got 3 hydrogen bonds, therefore. Do y'all know that 3 dots is therefore in science and math? 3 dots mean therefore. And on this AP test, they're going to want you to say a lot of therefores. So make sure you include a lot of therefores, because that's showing connections and that you understand it. So therefore, it has a greater viscosity. So what about temperature? I told you that the Valvoline commercial says that at high temperature, their oil is more viscous. So, and some of y'all know about this with syrup. Any of y'all like to heat up syrup before you put it in your pancakes? Some people do that. And some restaurants will serve hot syrup, and it's much thinner than cold syrup. You can imagine that, can't you, putting some syrup that? And it's because of this. High temperature means increased kinetic energy to overcome these forces. So temperature increase makes viscosity decrease. Velocity would increase. Okay, everybody imagining that? Excellent, y'all are doing great. Okay, now let's talk about another effect of all this, these forces. One is surface tension. Okay, so here we have some liquid and a bug who is standing on the water. You ever wondered how bugs can walk on water and you can't? It's because they are walking on to something called surface tension of the liquid, and you're too heavy. You would break it, but they're little enough they can do it. Okay. So on the surface, so here we've got water molecules. Everybody look at them, and they are experiencing hydrogen bonds to all the other molecules around them going down. Can you imagine that? But they're not experiencing it with anything in the air. Can you see that? There's nothing to do a hydrogen bond with. So all of their forces are going down and in. And that makes them very close together at the surface, where they're more spread out down inside. Down inside, the molecule has hydrogen bond all around. But on top, it's only down. It pulls the molecules close, down, and in. It packs them in tight. Can you imagine that? And that makes enough of a surface for the bug to stand on. It'd be like a concert where they got the mosh pit and everybody's packed tight. The star can jump on top and not fall through, right? Unless it's like School of Rock and everybody moves because it's Jack Black. But normally, everybody's so tight, they couldn't fall even if they wanted to. That's why the star can trust them, okay? So there's our little rock star bug. Okay, so on the surfaces, all forces are down and in. Molecules are pulled in. Surface area becomes less because they're all being pulled in. The result is what's called an elastic skin. Is it a real skin? No. It's just a force of all of these molecules stuck together so hard. Now, what are the attractive forces experienced by these liquids, both of which have high surface tension? So here we've got water, whose meniscus, remember what that is? The curve goes down. And here we have mercury, whose meniscus goes up. It bows up if you had a test tube of mercury, okay? So what is the difference? Water, what's making it stick together is hydrogen bonding. What makes the mercury stick together? What's it called? It's one of our 3 types of bonds. Ionic, covalent, and starts with M. metallic. So it's metallic bonding. Okay, and so what's the difference? Okay, see the figure it right. The meniscus looks like that because of the adhesive forces between the water and the glass are more cohesive than the forces between the water molecules, because that's just a force. It's not a real bond. The meniscus of the mercury looks like that because the adhesive forces are less than the cohesive forces between the mercury atoms. So here, this is more like a real bond, so they stick together harder. This is forces, and those forces can even be between the water and the glass, and it causes something called capillary action. And you would not be alive without it. One of the things that's the amazing thing about what life is based on. Yes?
Did you need to circle less twice?
Did I do it wrong? It should have been more in this. This one's less, that's correct. The other one's more. Oh, yeah, I did. I read it backwards than how it is written. Whoop, whoop, more fun with sound effects. Good job. All right, we good now? Okay. I was thinking about those molecules so hard. Okay, so this is called capillary action. If you have a very small diameter tube, the forces between the liquid and the wall increase the surface area. Because remember, why there's that skin is because it has to do with surface area. So the surface tension decreases and cohesion pulls the liquid up until gravity balances these forces. And that's how trees drink. Have you ever thought about how do trees get water out of the ground all the way up in that tall oak tree with no circulatory system to pump it? It does this. The little bitty tubes in the trees, remember the xylem and the phloem? It sucks up those little bitty tubes doing this, and it just crawls up all the way, even with the giant redwood forest. Isn't that cool? And if the trees didn't do this, they wouldn't photosynthesize, they wouldn't make oxygen, and you'd die. We got to have oxygen, right? We're in a symbiotic relationship with trees. I don't know. It's sort of one-sided. They make oxygen. I don't know that we do anything good for them. It's a one-sided, abusive relationship between us and the trees. But yay for the trees. We're glad. We're the parasites, I guess, using them for their wood and for their oxygen. Okay. Properties of solids, 3.2. So in your notes for this, I did not repeat the stuff about solids we learned last unit, but there definitely could be questions from it. So when you're studying for this test, make sure you look over the stuff about solids from unit 2. Okay, but we don't have time to repeat it. Just look over it. Okay, so what we're going to talk about first is a kind of solids. We'll call this A, covalent network solids. These are held together by extended network of covalent bonds. They're kind of like crystals, but instead of being ionic, positive, negative, what's holding them together are covalent bonds. And our classic example is diamonds. Diamonds are our classic example. So are they hard or soft? They're hard. Okay, B, another one is molecular solids. Okay, and they are molecular solids, don't have bonds. They just have intermolecular forces. IMFs, that's cool, kids. That's what this whole little thing is about. So an example of this would be like wax. Remember when we did our covalent versus ionic lab? And remember the wax? That's our molecular solid. It's only held together by IMF. So are they soft or hard? They're soft, like wax. And they have low melting points, where of course diamonds have high melting points, right? Very hard to melt a diamond. Okay, so that was B. Our next kind of solid we talked about before, but I put it on here, is metallic bonding. So, and how do metals follow the octet rule in bonding? They're in the sea of electrons, okay? So that's why I sort of abbreviated that a little bit. So we'll call that C, metal bonds. And so when you've got this sea of electrons going by, they feel like they have 8, because 8 are going by. Okay. All right, so next, molecular solids. We're sort of going back. So this is we're sort of going back to B again, because we want to talk a little bit more about molecular solids. Okay. Molecular solids consist of atoms held together by London dispersion forces. Remember, everybody gets those. And they can have dipole-dipoles. So this is in their as they are held together. And they can have hydrogen bonds. Okay. Now explain why molecular solids are soft and have low melting points. So the reason why is IMFs are not very strong, so they are relatively weak. Even if it's hydrogen bonds or dipole-dipoles, these are weak, so they melt easily like wax. But what about sugar? Does sugar melt easily? I'm not putting it in water, but heating it up. Remember when you heated it up in lab? Which one melted easier, wax or sugar? The wax, right? So what's going on with sugar? It's a molecular solid. Why is it so hard to melt? Okay? And it's because of this. Sugar, sucrose, is C6H12O6. So it's got all those oxygens, and each sucrose has 8 OHs on it, which causes 8 hydrogen bonds. And of the IMFs, remember the strong one is the hydrogen bonds. And that's why wax is soft and sugar is hard. Sugar is so much harder to melt. Okay? Everybody sort of seeing? That's our standard, talking about how we look at these microscopic things and how they make how we can see it in our macroscopic world. Okay, now let's go back to covalent network solids, our diamonds. We're back to them. We want to talk about them a little bit more. Explain why covalent network solids are much harder and have a higher melting point than molecular solids. It's because covalent bonds are much stronger than intermolecular forces. So any of these things they could ask you on this essay part of the AP test. And so for some of these, you'll look at them and you'll think, I don't know what to write. They want you to state the obvious. So don't write something. Write what's obvious. And because usually it's easier than you thought it was and you're overthinking it. They want just the obvious thing, that, that covalent bonds are stronger or something like that. Okay, so what are some more network solids? Silicon, germanium. Did y'all get to see silicon lumps in your honors class? I don't think I showed it to y'all. Remind me and I'll show y'all to them. They're very pretty. Quartz, quartz is hard, right? Good. Silicon carbide, boron nitride. So those are some covalent network solids. Now what about diamond versus graphite? They're both made out of carbon. They're called allotropes, meaning they're the same chemical, just bonded differently. And graphite, this is your pencil lead, the carbon is bonded in these sheets. In diamonds, they've got vertical bonds too, not sheets, not so plain. So here's the difference. Graphite has sp2 hybridized sheets. The layers slide past each other easy. The layers are only held together by intermolecular forces, delocalized pi bonds. Electricity can flow through this. And and it can conduct electricity. So this is how the scantron works. You color a little graphite, it zaps it. If the electricity goes through it, then it knows where you put your answers. That's why you have to erase completely, because if you leave graphite, it can conduct electricity. okay? Diamonds have tetrahedral sp3 hybridization. They're covalent bonds, okay? So, let's go on my thing here. Okay, so now let's talk about another one, silicon. So silicon is what they make computer chips out of. How come? What goes on here? Well, it is a covalent network solid and a semiconductor. So what they do is they put different atoms in it to control it, and it's called doping. I don't know why. It sounds like it's doing drugs, but they put something in it. They call it doping it. So there's two kinds of doping we're going to talk about. Here's our computer. If they add a little bit of phosphorus to it, then it does a little bit of, it does a little bit of substitution. This is called N-type for negative type. And it increases the conductivity. So they'll put phosphorus in it, and it works because phosphorus atoms, they'll substitute in phosphorus for silicon. Phosphorus has 5 valence electrons, silicons have 4, so you get an extra one, and that increases the negative charges in its conductivity. So we can increase we can make it conduct good with phosphorus. But the other thing is called P-type, yes, for positive. And what they'll do is they'll put aluminum in it. Aluminum has 3 valence electrons, silicon has 4, and it creates a hole where there was an electron and now there's not. So, and it's called the very scientific name of a hole. It makes, yes, you guessed it, a hole. You dope it and you make a hole. And the hole doesn't conduct, and the hole moves around the lattice, and so it's making not conducting. So how computers work is that it doesn't conduct all the time or not. You can turn the conducting on and off, and by turning the conducting on and off, you can code information. So then they can code it as zeros and ones, conducting or not. And does that make sense to some of y'all who know stuff about computers, that you can kind of see how that works? So that's what it's all based on. And I'm sure you can learn lots more in a computer class, but that's enough for us. All right, 3.3, solids, liquid, and gases. So most of this you learned in 8th grade honors physical science, so we'll go over this quickly. According to the kinetic theory of matter, kinetic molecular theory, the attractive forces between gas particles for an ideal gas are negligible. So we're not having any of these London forces. We're not having any hydrogen bonding. We are just flying around, not attracted to each other. See, our not attracted gases, okay? So let's review these questions about gas. Does gas have a definite volume? No. Does it have a definite shape? No. Does it expand to fill its container? Yes, right? Is it compressible? Yes, that's how pistons work. Does its particles flow readily? Yes. Is diffusion fast or slow? Fast. Is density high or low? Low. Everybody agree to that? That was not new information, was it? Okay, let's do it for liquid. Does liquid have a definite volume? Yes. I see nods, yes. Does it have a definite shape? No. Does it expand to fill its container? No. Is it compressible? It turns out it is slightly. Okay. Does its particles flow readily? Yes. Is diffusion fast or slow? It's actually slow. If I had a beaker of completely still water and I put a drop of food coloring in it, it would slowly spread through the water, right? Not real fast, okay? And is its density low or high? It is high. Let's try to make that a capital H. That'll look better, okay? Now, how about solid? Does it have a definite volume? Yes. Shape? Yes. Expand? No. Compressible? No. Does it flow readily? No. Is diffusion fast or slow? very slow. If anything diffuses through a solid, that's pretty amazing. Is its density high or low? It is high. All right, that was easy. Next. Okay, because the particles in a solid or liquid are fairly close together, sometimes you will hear this called that they are condensed states of matter. Condensed states of matter. Okay, that figure 11.2 is in your book, but just it says which one would have the intermolecular attractive forces appear to change as one moves from the periodic table. Okay, so what it's talking about is everybody look at the halogens. See how chlorine over there is red? That means it's a gas. See how bromine is blue? What does that mean? It's a liquid, and iodine is black, so it's a solid. So if we were going to talk about its forces, we would know that the one with the least forces would be chlorine, right? And then bromine, and then iodine. Okay? All easy, right? Okay, the kinetic energies of particles are usually controlled by changing the temperature. You heat it up, it moves faster. The dance goes faster. Describe what happens to the attractive forces between water molecules as water vapor undergoes condensation, turning into drops of liquid. Okay, so we got water flying around like a gas. It hits the door. It's cold. A cold piece of glass. What's going to happen when it hits to its speed when it hits that cold glass? Slow down. And what's going to happen to the distance between molecules? Are they going to be closer or farther apart? They're going to be closer. Are they going to feel more forces or less? They're going to start feeling more. They're going to start having some little hydrogen bonding. And then what are they going to turn into? They're going to go from gas to liquid, right? Everybody see how that works? Okay. So as the temperature decreases, it slows down and the kinetic energy will go down. Then they're going to get closer and intermolecular forces will increase. Condensation occurs as molecules combine to form droplets of liquid. Now explain about pressure. How does this affect it? Well, it's the same thing. You increase the pressure, it makes them closer. They get closer, they start feeling forces. That makes them more attracted to each other. And eventually the gas will become a liquid. You know how cursive L stands for liquid? You can do a little cursive. Some of y'all don't write cursive. Write a cursive L. Okay, we are rocking into 3.4, the ideal gas equation. The ideal gas is written, I forgot I'd already written it for you. PV equals nRT. We're talking heavy duty chemistry. There's the song. The gas laws are good to know. You can use them everywhere you go. We're talking PV equals nRT. We're talking heavy duty chemistry. I did not write that song. You're thinking that is a lame song. I bet Miss Blackburn wrote it. No, I went to a science teacher convention in New Orleans and I saw the guy who wrote it perform live. I know you're impressed. I could put the link on our canvas to all of his songs. You could sing along. Okay, if we use a value, everybody put a little bracket here, right? AP. These notes sort of came out of your book, and your book is for college, but what we care about is not so much college, but the AP test. Everybody remember when we learned this in honors, remember how we learned, one of the first things we learned is that there are a bunch of units for pressure. There is atmospheres, there is millimeters of mercury, there's inches of mercury, there's torr, there's bar. Remember all of this? So starting to feel, do y'all remember why there's so many units of pressure? It was because if you remember Joseph Priestley and Anton Lavoisier, remember Priestley, the minister who's the father of chemistry, which is kind of funny. None of y'all expect your religious leader to be just on his spare time starting a whole new branch of science, but that's what he did. But remember, we saw a video and Anton Lavoisier did academic plagiarism and stole his work and published it, but he understood it a little bit better, and so some people call him the father of chemistry. And if you remember, what they studied first were gases. Remember the heavy air, the air he talked about? They discovered carbon dioxide. Remember he said they're pouring the water over the beer vat and it made bubbly water. And so the very first thing I learned about were gases. And we have to say that we forgive Antoine Lavoisier for doing academic plagiarism because he got beheaded in the French Revolution. And so, and he did an experiment when he got his head chopped off. So for that, he gets to not only be the father of chemistry, he can just be king of science because he did an experiment once his head was off his body. So for that, we forgive him for everything. And the government of France later wrote a letter to his family apologizing for beheading him, saying that was a big mistake, chopping the head off of one of their greatest scientists. So anyway, French Revolution. So, but all that is to say, there's all these units, because this was being discovered all over the world by different scientists sort of at the same time, and they all made up their own units. So that's why there's so many. But on the AP test, there is only one. It is this. On the AP test, they use for R, for the ideal gas constant, this number. This is going to make life so much easier, isn't it? Now in college, you might have another one. But that's what they use on the AP test. And for pressure, they only use the units of atmosphere. So much better. And they only use volume in liters, and temperature, of course, is in what? Kelvin. That's where they're going to try to trick you. Remember, this just isn't a test. It's a game. They try to trick you by seeing if you forget to change to Kelvin. So don't forget that. Okay, so in your book, sometimes they use this, and sometimes for pressure they'll use torr. We don't really care about that. All I have to say about that is if you're using your book to work problems, don't for this. For other units, it'd be fine. Your book has problems and the answers in the back of the book, so it's a wonderful resource. But for these ideal gas problems, let's just stick to the ones I give you in the I Do We Do's and the one on the College Board website so that we can really get in our head these values and how to use them. Okay? So for this one, no book work. Okay, so here's an example problem. It says, use the ideal gas law to calculate the pressure. So pressure is what I don't know. That have my question word with it, calculate. Now, whenever I do word problems, I always annotate them. I label everything, all my knowns and unknowns, because I get so excited about doing math that I'll just gallop off in the wrong direction and I'll solve a problem, but it won't be the one that they ask for, okay? So I have to make sure that I'm actually answering the problem they ask for. Okay, so what's the pressure inside of a helium tank that has a volume, there's my volume, and contains, there's a mass, okay, and we have a temperature in Celsius. So what should I do very first? Turn it to Kelvin, so I add 273, so this is 295 Kelvin, and that's my temperature. Now, in my equation, PV equals nRT, do you see mass anywhere in there? No. So what am I going to do with that 30? What do I have? Look, pressure is my question mark word. I have volume. I've got my constant up there. And I've got the temperature. What do I not have? N. What does N stand for? Number of moles. A lot of times in math, N stands for number, which is kind of funny because it's all numbers, right? But it's number of moles. Can I get the number of moles for my grams? Why, yes, I can. So I put 30 grams. I divide what goes with delicious graham crackers, the M&Ms. So helium is 4. So this is equal to 7.5. So that's N. Now I've got everything. So what I do next is I substitute in the numbers for the letters. Now I sing a song, Substitute. It's by The Who. It's from before my time, so it's before your time. But it's more fun if you sing, and it helps you remember what to do next, okay? So listen, other science teachers, in particular in the school, if they have an equation, they will first rearrange it for their unknown variable. then they substitute. I don't do that, and I'm very passionate about not doing it, and this is why. I not only teach chemistry, I teach physics, and I teach math. And all of those have equations associated with them. I know hundreds of equations. I've memorized them. It's very convenient as a STEM person to have memorized lots of equations. I don't have to look them up. If I rearrange this and I solve for P and divide both sides by V, then I have a new equation. P equals nRT over V. If I solve for T, then I'd have yet another one. T equals PV equals NR. I'm not going to memorize it if this thing is 5 different equations. If I always use it straight, is what I call it, and I always substitute my numbers in next, I end up memorizing all these equations. So the other teachers who are against this and they like to rearrange first, most of them only teach one subject, that does this. Like Miss Raymond only teaches physics. She doesn't teach math. She doesn't teach chemistry. So I think I just think this has helped me so much, and I highly encourage you to do it my way and not theirs. I see why it works for them, but I like it much, much better to put your numbers in next. Okay, my little soapbox there, had to have it. Okay, so I'm going to do my substituting. I put my P for my unknown. My volume is 17.8 equals my number of moles is 7.5. My R is up here, 0.08206, and my temperature is 295. Now I'm ready to do my math. And how you get a variable by itself is by doing the opposite, is being multiplied by 7.8. So what's the opposite? Divide, and what I do to one side, I do to the other. So I'm going to divide this side by 7.8. Those cancel out. I divide this side by 7.8. I put my calculator 17. If you write too messy that you can't read your own writing, that's a problem. So 7.5 times 0.08206 times 295, enter, divide by 17.8 equals, to sig figs, 10 atmospheres. Put a box around it. If you have the right answer, they are going to be way less critical of your math. Do you see that? Now, if I was on the AP test, I would include units with this to make it prettier. But, honestly, it's all going to work out, especially when I know these are going to be my units, because we're not doing any other units for AP. Okay, one more, last problem. If I can do it real fast, then we'll finish. Okay, so this is what I wanted to show you. Do you see how this is the combined gas law? P1 V1 over T1 equals PV V2 over T2. You don't really have to memorize that. If you think about that, this is the ideal gas law set equal to another ideal gas law where you mark out the stuff that aren't important for that problem. So if I have PV equals nRT, and I want to just have the P, the V, and the T and mark it out, then I divide by T, and then those don't matter, so I'm marking them out of this, and I'll mark out that. Do you see how that's half of the equation? And do you see this always works? If we're doing Boyle's, look, there it is. If we're doing Guy-Lussac, there it is. If we're doing Charles, there it is. So you don't really have to memorize all of them. You can get them all from ideal. So here's one of these. So we got P equals P2V2T2. I'm going to substitute 1 atmosphere, there's a pressure, I'm doing this quick, times 30, that's my volume, times my temperature plus 273 is 298, equals my unknown, that's what I'm looking for is pressure, times my second volume over my second temperature is 254. So first get rid of the denominator, because that's what's making it ugly. Multiply both sides by 254. Those cancel out, then divide by 55. Those cancel out and you have P. Multiply those, divide by that, and pressure equals 0.46 atmospheres. Whoop, whoop, whoop. More fun with sound effects. And that's where we're going to end. Science is great.